Okay, good afternoon. I hope you got good lunch and good rest before coming here. Is that okay? All right. So what we'll do right now is I'll finish the morning's presentation, and then I'll then move to the next chapter or next uh, topic, and hopefully we'll have enough time to take care of both things. So we were talking about putting capacitors in the system, and this graph is where we stopped last time in the morning. So basically, what it shows is that in terms of the number of capacitors, it's not necessary that you have to put too many capacitors, because if you put too many, then you start to lose the effect. So there is a best number, but again, look at the numbers here. You can see that the difference between 9 capacitors and 15 capacitors, the cost is not really a huge difference. So you may actually say, okay, let's just put 9, because there would be some other maintenance issues that will be have to be taken into consideration. So obviously, from 7 to 9, you see a big drop, but then it slows down after that. At 15, it bottoms out. Okay. Now, in terms of uh, how to use these capacitors, actually, the capacitors can have two types of controls. One is that they can be fixed or they can be switched. The fixed capacitors are those that are needed uh, even at the lowest load, and then you keep them on, and then as the load increases, then you have some kind of like algorithms to switch them. So when the load exceeds a certain value, then you switch one set of capacitors. Then if the load increases further, you switch another set of capacitors. So there is a schedule that you can, like if you have a daily load, you follow the load, and then based on the load, you decide how to switch the capacitors. So every day, it will be a different situation because the load will be different for different days. So you don't have a predetermined schedule. In the old days, when if you don't have automation, then you use a predetermined schedule. But if you have automation, then you can do these things in real time. Okay, so next topic in our discussion in automation is restoration, system restoration. Now, system restoration, I talked a little bit about that in the morning, where we have a problem and then we open the breaker on one side and we close the breaker on the other side. Now, that works in a situation where you have a small outage in one location, you isolate that area, and then you provide power from the other side. In the meantime, fix the problem and then restore the system. But if you have a problem in the system that takes out a large part of the system with not multiple, but say for example, you have a problem at the substation or the grid has a problem, so the outage can extend for a longer duration, and also it may cover a larger area. And in those situations, in particularly if you are looking at a condition where it's a hot day, for example, and you lose power, then everybody's air conditioners that were working will stop working, and the house will become hot. So these are what we call as thermostatically controlled devices, which are air conditioners, heaters, and refrigerators. They have a control mechanism. So in your own home, when you look at the air conditioner, you set a temperature. Now this air conditioner is not running continuously. It runs for a little bit, and then it shuts off. The fan itself is running, but the cooling air conditioner itself is not running continuously. It runs for a certain time and it goes off and then comes on and goes off and so on and so forth. So what happens is that if you are in a situation where you have outage of a long duration, and then uh, for a longer period, even for like 20, 30 minutes, the rooms will become very hot. So when you turn the power comes back on, everybody's air conditioner is running, will try to run at the same time. In normal operation, what happens is that air conditioning in this room is working, the other room it may not be working because that is it's a cycle. So because of that, there is a natural diversity between operation of air conditioner. So maybe at a given time, 50% or 60% of the air conditioners are running, the remaining 40% are not running. But when the power is restored, all the air conditioners want to run at the same time. So what happens in that process is that the load on the grid, the feeder will go beyond its capacity. And also the transformer will become overloaded because you're looking at a much higher load for a short duration. So this is where the what we call as cold load pickup situation. And this typically is experienced after extended power interruptions. And sometimes, as I showed you in one of the examples just on Monday, that the load at the point of restoration could actually be two times as high as the normal load. So in that case, you have to worry about, is that going to be too much for the transformer to handle or the feeder to handle, or is it, or is there another way to do it? So one particular option is to do restoration in steps. Pick part of the system, wait for a little bit, pick another part, and so on and so forth. So what we're going to do is I'm going to talk to you about a process where we'll use step-by-step restoration. Now, talking about cold load pickup, we already have discussed this a little bit, so I'm not going to discuss more. But we are not concerned about the first three phases, which are transient phases. We are more interested in the steady state phase where the load itself is going to be high for a certain time and then it starts to decrease gradually. So, and this issue has become more pronounced because when I think right now in India we are seeing a lot of air conditioning being used. In USA in 40s and 50s, not as much air conditioning was used in those days, but now every home has air conditioning because the fact is that the climate has changed, things have become hotter, and better air conditioners are available. In the old days, the air conditioners were just being like it was a luxury in those days. Now it's become a necessity. So everybody uses them. So therefore, this issue has become important not only for US but also for India because we have a lot of air conditioning and air refrigerators also have the same phenomenon because they also have cycling inside. But as if you interrupt the refrigerator for a long time, then it's going to run for a longer duration until it cools off a little bit. So this is again repeat of what I showed you last time, and I just want to show that again because this will be important for the rest of the discussion. So the top one is a model of, it's not a model, it's an actual recording of data after an interruption. So you can see that the initial load was almost 2 times the normal load here, and it took close to about 30, 40, about half an hour from here to here to come down. That's because gradually the cycling of the heaters will start happening and the load will come down to a normal level. So for mathematical purposes, we can model this as a delayed exponential function. So you initially, when you restore power, all the load is going to stay at a higher value, and then gradually as the houses start heating or cooling, reach a particular set temperature, they'll go off, and not all of them are going to go off exactly at the same time. So they'll be staggered. One of them will go on first, and then another group, then another group, and so on and so forth. So as a combined effect, we can say that it will be a function which looks more like an exponential function. So this is kind of standard model that is used in modeling of cold load pickup, and this was introduced by some people in early 70s, and we adopted that for our research. Oops. And used it to determine some uh, approaches for restoration. The impact of cold load pickup is it has an impact on operation and design, because if you were to design and if you were to include cold load pickup in the design, you want to make sure that you have enough capacity to take care of cold load pickup. And we don't want to include a capacity which is going to be able to allow to switch everything in one step, but in multiple steps. How long will it take for you to restore the whole system? That's the question. So we can plan things accordingly. Also, what happens is that uh, cold load pickup can also result in extra voltage drop, because now you have higher load on the feeder. So load is 2 to 3 times the normal load, and that's going to cause voltage drop. So it's possible that the people at the end of the feeder will see a voltage which is lower than what it should be. But one good thing is that the ANSI standard that I talked to you about allows you to reduce the voltage under emergencies. So instead of operating at 0.95, you can go all the way down to 0.9. So extra voltage drop is permissible during emergency conditions. So, and of course, in terms of the system analysis, urban systems in general, overloading of transformers is more critical because the feeders are not very long in urban systems. So the voltage drop does not necessarily create a problem, but before that, the transformer loading will be a problem. But for rural systems where the feeders are very long, the loads are not very large, in those cases the transformer loading will not be an issue, but voltage drop will be an issue. So you have to consider either if you have an urban system with a thermally limited situation, so then you have a different process for restoration. If you have a system with long feeders, it's a rural system, then you have a different process for restoration. The process is the same, the criteria changes a little bit. And of course, what we try to do is we try to restore the system in steps. So what we need to find out is we need to uh, consider load behavior and from that determine the restoration sequence. And then we need to know what are the load dynamics, like what kind of model. Of course, I showed you the model, but how long does it remain constant, and then it starts to decrease as an exponential function. So we need to know the parameters of the model, like is it first 10 minutes, 15 minutes, and what is the rate at which it's going to decline exponentially. Now, these are some of the things that are included in the optimization process, and then objectives are to meet the restoration goals while limiting transformer and feeder loading and preventing voltage drop violations. And essentially what we are trying to do is minimize customer interruption duration. We want to restore everybody as quickly as possible without overloading and damaging your equipment. So on the one hand, you have to worry about loading of the equipment. On the other hand, you have to worry about how long can the customer stay without power. And of course, this has a direct impact on the system reliability, because shorter interruptions lead to higher reliability. Now, these are the operating limits. The transformers typically are allowed to be overloaded, and basically what happens is that the transformers are designed with multiple levels of operation. Like you have natural oil-based cooling, then you have one level of fans and another level of fans. So you have 3 separate levels of operation of the transformer. Now, the IEEE PC57.91 standard, it allows transformers to be loaded beyond the highest rating for a short period of time. You can actually load, like for example, if you have a transformer that's rated 12, 16, 20 MVA, so 20 is the maximum at maximum cooling when all the fans are on. You can actually load the transformer double of that to 40 MVA for a short period. But the problem is that that loading can be done only for 30 minutes. And then you have to shut down the transformer because it gets too hot. So you can use it for half an hour, but you have to shut it down. But if you load it to 1.5 times the value, which is instead of 20, you go to 30, then you have more time, a few hours before the transformer becomes too hot. So what you have to do is you have to set a limit in terms of what is the maximum loading that you want to allow on the transformer for a short period of time. And also, anytime you do that, it will also result in extra loss of life. Because when you operate your transformer at a higher temperature, it will result in loss of life. So there are some formulas that are available to calculate that, which is part of this standard, that you calculate the loss of life, and then any emergency operation, the transformer loading should be controlled in such a way that the loss of life does not exceed 4%. Otherwise, if you consider 4%, and if you operate the transformer at that high loss of life, then within a few years, or if you repeat that multiple times, you are actually going to lose the transformer very quickly. So that's why we limit that to 4%. And then also there are some limits on temperature. So maximum top oil temperature is not allowed to exceed 110 degrees Celsius because the transformer is inside a tank. So the oil becomes hot. The top part of the oil is hotter than the bottom, and the oil circulates. So the top oil temperature should not exceed 110 degrees. And the windings, which are very close to the core of the transformer, the hottest part of the winding should not exceed 180 degrees. So basically, all these things are done with calculations, but you could actually, now they are putting, they have devices, sensors that can be embedded inside the transformer to in real time measure the temperature of the oil as well as the windings. So, and then as far as the feeder themselves are concerned, typically feeders can be loaded up to 133% of the normal load. That's industry standard. And then as far as the supply voltage is concerned, we can exceed the voltage drop by, like instead of normal operation, you allow 10%, and 7.5% is on the main feeder, 2.5% on the lateral. In emergency, we can allow 3.54% on the lateral, and correspondingly the voltage drop on the main feeder will also be increased. So I think I have some data in the next thing. So yeah, main feeder in emergencies, it can go up to 10.62%. Because what you are saying is that we can operate from upper end, which is plus 5% to minus 10% now. So you have a 15% operating range instead of plus 5%, minus 5%. So you have extra 5% on the lower side. We don't increase it on the higher side because you can't exceed more than 5%, but you can allow the voltage to go down by extra 5%. So again, during short interruptions, we don't worry about cold load pickup, but it is important for longer interruptions. So in terms of an example here, we were assuming that we have, so this is a case where I'm going to show you some results to tell you what we have done. So what you see is, see what happened, okay, right here. So this is the transformer right here. This one is the substation transformer. And then you have 1, 2, 3, 4 feeders coming out of the transformer. And then on the bus here, and then each feeder is divided into 3 sections by putting sectionalizers in between. So we have an option of closing these devices separately. And then as far as what we are assuming is that these are can be controlled remotely. So you don't want to do manual operation, but you have to do automatic operation. And then also what we are saying is that in terms of restoration, you have options like if you close this breaker and you can close this as well as that, so supply power to all these 3 sections at the same time, or you can close this breaker, you can close this breaker, keep these 2 open, so you can possibly just pick 1, 4, 7, 10 in the beginning, and then you close the switches in whatever order you desire. Now the problem here is that depending on how you close these switches, it can, if you don't select the order properly, it can take you much more longer to do it compared to using an optimal approach where you can very quickly restore the switches. And also, with another thing that is important is that you need to consider if any of these sections have any priority loads, for example, a police station, hospital, or a fire station. So in that case, you may have to override the optimal solution by saying that because there is a priority, we need to fix this feeder first before we go to the other one. So let's see. Okay, I already mentioned all these things. They are written. Okay, so we have constraints which are precedence constraints and priority constraints, and then we are looking at restoration only on the main feeder, not talking about laterals because laterals will be included as part of the main feeder. So okay, I think there are some things you can read on your own. This basically simply says that it is not very feasible to put switches on the single phase feeders because they are more expensive. But 3-phase feeders, the main feeders, if you put sectionalizers, they can be not only used for restoration, but they can also be used for other protective operations. And then this is a little bit of math here. I'm not going to try to prove everything because that will take a long time. So this is the same function, delayed exponential model. So what we are assuming is that at t equal to 0, the power goes out. The system is out of power for duration, which is Ti. At Ti, we restore the system. The power goes to, the demand goes to SUI, which is considered the undiversified demand, and SD is the diversified demand, and then the load stays constant for a short duration, and then gradually it comes down to a value which we call as the diversified demand. So you can see that we can write, and of course what we are assuming is that this alpha here is the exponential, that function here, and alpha is the rate at which the exponential function is going to decay. So it's part of that thing. And then the this u here is the unit step function. I don't know if anybody who has done electrical engineering will know unit step function, which is just a step function. So basically what we are saying is that when you multiply it by unit step function, anything outside of that at t less than ti, small ti, things will go 0 and it will stay 1 after that. So same thing here, u T minus big Ti basically is a step function at Ti. So only things which are, when you multiply it by that everything else before that goes to 0. Now, I won't show you the full derivation and how we obtained it, but this is something, if you have time, you can. Now, I'm not going to ask you this in the exam. It's too difficult to worry about. Don't worry about that, because you might be wondering if this will come in your exam on Friday. It's not going to be there. These equations are not going to be there, because that it's a little bit more than what you can do in 1 hour. Okay. But if you are interested, you can try to prove that this is equal to this function that's shown here. Okay. So, and then the idea, central idea is right here. So what we are trying to do is this picture here on the right here is what we are looking at, where we say that SMT is the maximum load that we want to put on the transformer. That's the limit. We don't want to exceed that SMT because of the fact that we don't want to hurt the transformer. Okay. So then what happens is that we have total of this example has I think I'm trying to remember. Okay. M is let's see this. Okay, so you want to restore all the n sections can be restored simultaneously if the load does not exceed the transformer loading. So what we do is, in this case, we say that we pick a combination of the sections that can be restored in the first step, and we add their load and look at the condition that it should be less than equal to SMT, which is SMT is the maximum allowed load. So the sum of the sections that are restored in the beginning should be less than SMT. So in this particular example, we are showing that it's a 9-section problem. So 6 are restored in the beginning and 3 are restored later, as an example. So in this case, the 6 that you selected had a load which is equal to this, which is less than SMT. If you had added one more, then it would have exceeded SMT. So we have to limit to 6. And then initially the load stayed at this level, and then it started to go down, and then it came to a point where adding one more section was feasible, because the next section, if you add load of that, it will come to a point where it is just about SMT. And then you wait for because this is already decreasing. So in this case, the load will not have a fixed, like a constant value, but it will start to continue to go down because this is already going down. But the combination of the two will change. It's a sum of a function that is going down plus a constant value. So it will have characteristics like this, and then it will continue to go down further at a higher rate. And then here another point comes in where you can restore another section, and so on and so forth. And ultimately, once you have switched 3 of them, the load is going to come down. So this is how the load is going to look like when you do step-by-step restoration. Now, the question is which 6 to restore first, which 3 to restore later. So it's a problem that has so many solutions. Yeah, we have to pick the best one. Okay, so I think this is, I already talked about that, so I'm going to skip that. And so this analysis that we did, we assume that each section is assumed to have approximately the same characteristics, load decay characteristics, although they have different load values, because one section could have larger number of houses compared to another one. But as far as the exponential characteristics are concerned, we assume that to have the same values. Okay, and then we look at this. So this is the ST is a summation of the loads of the feeders, and I think this is again, it basically what it is telling us is that it's the sum of the different sections, the load of different sections. And again, this is a little bit more involved thing here, because what happens is that in the previous slide, I showed you, not the previous load, initially when I showed you load of one section, now here you are adding loads of different sections where the time, the individual sections are shifted in time. So you have to account for that shift. And then once you do that, so this ST is the sum of M feeders. Okay? And then this one is a combination of all the sections put together. And again, this is a general equation that is can be worked out based on different sections that you have in the system. So there are, it's a summation of M feeders, and then we can also analyze, determine an analytical expression for restoration times TOJ for each section if alpha j, alpha 0 values are the same for all the sections. So this is a specific condition that is can be implemented, and then again, this is a derivation is not important here because it takes a lot of effort to come to that point. But ultimately, what happens is that if we have that one condition where the rate of decay of the exponential rate of decay of all the sections is identical, then the calculations become very simple, very like they work out. You get a closed form solution. So this is the solution. TOK is the time of restoration of different sections, and you can see that 1 over alpha comes out outside and everything else is kind of inside, and there's a natural log here. So anyway, I think moving along. So what I'm going to do is, as I said, that this is optimal operation and design while considering CLPU is important. So in terms of design, you want to make sure that you have enough capacity in the system to handle such situations. And from operation point of view, you have to make sure that your transformer and the limits are kept in mind, voltage drop is kept in mind, and you come up with a restoration sequence. So as an example, what we did is we considered 12 sections, and this is the data for different sections is included here. And we consider that the transformer is rated at 35 MVA, 30 MVA under FOA conditions, and then we are allowing the transformer to be loaded to 45 MVA. And then delay part of the cold load pickup model for each section was considered to be 20 minutes. So this is an example. So when we did the analysis, we found that the search of all possible combinations of restoration, it shows that if you select the sections for restoration, you can restore the system in 83 minutes. And if you don't follow the optimal solution, then it takes 93. So minimum is 83, maximum is 93. So the difference is not, it's only 10 minutes. But 10 minutes, when you have to stay out of power for extra 10 minutes, you can realize how happy you would be if you save 10 minutes. So it's an important consideration. And then what we did is we said, okay, let's change the loading of the transformer to 36, the maximum loaded from 45 to 36. In this case, you have to wait longer because now we have to reduce the number of sections that can be restored in the beginning. So it turned out that in this case, the maximum time turned out to be 195, and the minimum time came to 168. In this case, you can see that the difference is significant. So it's about half an hour extra it will take to restore. So that's why it's important to find the best optimal sequence of restoration, and this is how the sequence turned out to be 10, 7, 8, 9. And then if you go back to the previous slide, you can say, let's say 10, 7, 8, 10, 7, 8, 9. So, oops. So this is section 10, 7, 8, 9, 4 was picked after that. So you start with 10, 7, 8, 9, 4. So that combination of sections gave you the best option. So this is the case where we did not look into voltage drop concerns because we are looking at an urban system. We said voltage drop is not an issue. But if you were to have a system where voltage drop was a problem, then we can, we did another example of a system where we consider that voltage drop is an issue. In that case, what we did was well, this is a design problem. So when you design things, you have to do a lot of assumptions. So what we assumed is that each feeder is providing power to a triangular area, and in triangular area you have approaches where you can find equations for voltage drop in a triangular area. There are standard methods available. And then what we want to do is we want to find the location of the switches here and here that will provide you, because what you want to do is during restoration, you want to close the circuit breaker which is at the substation first, then close this switch, and then close this switch, and you need to know where should you locate these switches based on the most probable conditions as far as the restoration is concerned. So what we did was, for an example case, we used this system with at 12.47 kV, 2 square miles, 3.61 MVA per square mile. Substation spacing was 4.56 miles, and the main feeder was of 3.4 miles. Feeders per transformer, 3 transformers, and we used these specific conductors listed here, and we assume that there are going to be 0.2 events per year, which essentially means that you can't have fractional events in a year. So it means that you have one event in every 5 years. So that's how the frequency of events is computed. Okay, then what we did is we did this analysis, and we found that this particular system that has the data in the upper table can be taken care of with a 30 MVA transformer, and the first switch is placed at 1.686 miles, the second switch is placed at 2.12 miles, and the switching times are the first, you close the substation switch, wait for 30 minutes to close the second one, and wait for at 60 another 30 minutes and close the next switch. So this will allow you to meet the requirements of cold load pickup given these conditions, this is something that one has to be able to kind of like based on the models that we considered. So this is an example, and it does not necessarily exactly apply to every system, but if you have data for your own system, you can compute things that would be needed. So that, and of course we considered the study duration to be 30 years, and if anybody is interested in these details, I can point you to some papers that we have published on the topic. So anyway, so this is at the end of the things that I started in the morning. So let's just have a few questions on this new material before I move to the next one.
connected load, the undiversified load ST value then.
ST is actually, we're talking about the this SU.
And SD, these numbers.
So these are the values that one would have to do experiments in your own company. You have to actually run some experiments to do it. Or like for example, or it's typically hard to force an outage, but if you have enough instrumentation in your system, and if an outage happens to happen, then at that point you record the data. But it's very difficult to do it for individual homes and feeders, but you can do it for the entire system that has experienced an interruption. For example, the data that I showed you here, this came from an actual utility company, the one that I showed you at the top. So this company kept track of the data when an actual outage took place. So if your utility wants to get values of SU and SD, they will have to put meters to be able to measure those things. Anything else?
And the load varies sometimes, like one example said 45 MVA and then other simulation was 36 MVA. So are these data from simulations or?
No, this is based on your own judgment. Because as I said that the transformer maximum loading is 30. So one company says that I am more interested in helping my customers and I am ready to do a little bit more life of my transformer. So they say we're going to load it up to 1.5, which is 45 MVA. So 30 times 1.5 is 45. So you get a different solution. Now the other company says that we are very conservative. We don't want the transformer to become too hot. So we are going to load to 20% overload on the transformer. So that 20% of 30 is 36. So that's how it's a judgment call. It's not like anything. No. That's what actually the problem that I was talking about is that this restoration for a thermally limited system, you can do real time if you have enough measurements available in the system. So it can be done real time. But this one where I said that you want to do a design problem, this is something that you are doing it for a system that has not yet been built. So you're designing a system. So this one is not real time, but this particular case where we have the actual times available and everything, this can be done in real time because this is an actual existing system and you're trying to operate that. Okay, so next one, again, basic starting slides of acknowledgements and so we're going to talk about renewable energy resources, the next topic. Why talk about renewable energy resources? Because the prices of distributed resources have come down, and so it is becoming attractive to deploy them in distribution systems. Typically, otherwise distribution systems don't have any generation. They are simply loads. Power flows from the generation to a substation and radially it goes into the system towards the load. But now because of the technology being more advanced and the materials are there and the cost has come down, so it's becoming attractive for people to put solar panels in their homes or any other kind of distributed resources that can be put in the system. Now, in terms of when we look at distributed energy resource, this is something that these are small generators, small resources that have to be directly connected to distribution system. So it is you have a transmission network, but this is connected at the lower voltage level, which is at the distribution level, and they are typically less than 10 MVA. They're small in size. Anything bigger than that is not really a distributed resource. Distributed resource is a small size. So 10 MVA is typically the defined cutoff for distributed resource. So this is IEEE distinction. Now this can be any kind of, it can be generator, it could be any energy storage devices like batteries, for example, that are capable of injecting power into the system. So that's what is called a distributed energy resource. So typical examples include rotating induction or synchronous rotating machines. They can be driven by diesel generators. Like diesel generators are also considered or distributed resource if they're small. It could be natural gas, biogas, propane, wind, or even water-based hydro stations, small ones, or it could be other types of pipe. Forgot to mention wind and water, both can be there. And then static type can be solar, photovoltaic, or batteries. So these are some examples of distributed resources, and most of them are connected to the system through a DC. It is you have to have some kind of power electronic interface, even if it is generating. So in most cases they are connected to a power electronic interface, and they are inverter based resource. So any distributed resource that we have in the system will be inverter based resource. So sometimes you will hear terminology like IBR. IBR, inverter based resource, can also be put in transmission systems, because if you have a wind generator, although it's a rotating machine, but the rotation is not at a fixed speed, so you have to convert it to from one form of AC to DC and then come back to AC. So even in distribution system, all of these devices, except I think most of them are connected to the grid through a power electronic interface. But some of them, if you have a diesel generator which has a synchronous generator, they can be directly connected to the grid. So I mean, I said not all, but most of them would be. So the anyway, so coming back to the main topic, so most of the resources are through IBR, but some of them could be directly synchronous generators can be connected. But most of the current trend now, hardly anybody uses diesel generator these days. If there is something existing, an old generator is sitting around, they can use it, but usually people don't buy a new diesel generator. It's kind of like not the best thing to do. So anyway, the wind is one of the possible distributed resource, but wind generator, actually 1 megawatt is the lowest size that you want to buy, because anything smaller than that is not very efficient. So in terms of its application, people like us, we can't be putting a wind generator that is a 1 megawatt. It's too big for us. And of course, also another concern is that you don't want to put a windmill in the middle of the city, because that creates a lot of other issues, social issues, and that could also create some noise and other wind related issues. So in urban setting, wind generators are not suitable. So, but in Rural communities, as I said, in Kansas, we have small villages where you have a small population. We can put a wind generator of 1 megawatt, and that can take care of the load of the entire city. So in rural settings, it's possible to do that, but not in a urban environment. So the in terms of the capacity of the wind generator, it basically uses wind to rotate the blades, and the equation that creates the amount of power that is generated, PM, is 1/2 rho times A V cube times Cp, where rho is the air density in kg per meter square. A is the area swept by the blades, like you have a circle that based on the size of the blades, and V is the wind speed in meters per second, and Cp is the power coefficient. For blades with length L, the sweep area is pi a square meter square. So this is the standard equation that is available for power generated by wind generators. And again, as I said, that wind generator mostly use doubly fed induction generators, and they don't run at constant speed. So whatever the voltage is generated, you have to connect it to a power electronic interface, convert it to DC, and then again have another converter to go from DC to AC. So, and that AC at the last stage is at the standard 50 cycles, and then you have a regulation in terms of either you control in terms of control mode. It can be either grid following or grid forming depending on the application. Typically, in a distribution system, if you have a wind generator, if you are grid connected, then you will be using grid following. But if you get wind, you can do grid following, grid forming also in wind. So same thing. It can be any kind of generator. You can, so long as you have a power electronic interface, you can do that. So that's the way the wind generators are operated. And this is a graph that shows the output of the wind generator. Now, notice that with the speed is below a certain cut-in speed, it's not going to produce enough power. And also, so this is the graph that goes from minimum speed to the maximum speed. And this is the rated speed, which is actually takes you to the rated power, but any speed increase beyond that does not increase the output. But there is a speed called cutout speed, which is basically the speed which is the maximum allowed, because beyond that there is a danger of the wind getting damaged. So you actually block the generators if the wind speed goes beyond that. So this is the characteristics of a wind generator. Now, as far as the solar generation is concerned, we have there are two types of solar generation, which is one is the solar photovoltaic and the concentrated solar power. But concentrated solar power is typically for very large capacity. It's not suitable for whom we're talking about multi-megawatt type units, which can be placed in a remote area in a desert, and you can shine the use mirrors to shine the light on a molten salt column and all those kind of things. So it's a very completely different approach. There are some plants like that in many countries. There is one in US, there is one in Spain, but they are for transmission line applications. For distribution system, they are too big, so we don't need to worry about it. But photovoltaic is the option, that is the common option for distribution systems. And they range anywhere from 200 watts to, can go up to multiple megawatts. But in a distribution system, you are looking at 200 watts to 10 megawatt, because distributed resource limit is 10 MVA. So you don't want to go beyond 10 megawatt. Now 10 megawatt itself is pretty big for a distribution system. And of course, an individual homeowner will not be able to build a system that big. It's somebody, a commercial operation, like if they have a huge shopping mall or something, and they put a lot of solar panels on the top of that building so they can generate a lot of electricity. But 10 megawatt is still a pretty large number. So this is mostly rooftop installation in general, because you want to maximize the usage of space. So you don't want to, if you put things on the ground, you take away space from agriculture and other things. So rooftop is the best place for it. Now this picture is kind of like an example of how things look. And this is from a small place in Germany. If you go to Germany, go to any place, you find homes and business. Everybody, this particular town, every building has solar panels. You talk about it. It's just full of houses, businesses. You walk around anywhere, everything has solar panels. So this is kind of like the way of the trend of the future. But the problem is that it's not that easy to have solar generation at in the distribution level, because there are issues of how big can they be, where should they be placed, and are they going to have some negative impacts on the utility in terms of reverse power flow, voltage problem, protection problem. There are so many issues are there. These are the technical issues. Of course, on the economic side, so there are three concerns here. One is the technical concern. The second one is economic concern, that it has to be economically viable. So if you invest money to put solar panels in your home, you want to make sure that you're going to save some money. It's not that you're going to just put there and say, oh, I'm okay with it. So that's the economic aspect of it. The third aspect is social aspect, because what happens is that some people like it, some people don't like it. So some cities, I don't know how the regulations are in US, in India, but in US, where I live, I want to put solar panels in my house, but I'm not allowed to do it, because that area where we live has a homeowners association. Like if you live in a colony and a colony has a society, and society has ruled that nobody can put solar panels. So what do? I want to put it, but I cannot put it because social acceptance is not there yet. So this is also an issue. You cannot suddenly say, even if something is technically feasible, the social aspects have to be taken into consideration. So particularly for solar energy, these three things, the technical issues, economic issues, and social issues are important. Now from the technical side of things, this is the equation that determines how much power is going to be generated by a solar cell, a PV cell, which is a PN junction electronic device built on the principles of Schottky barrier. So those of you who know a little bit of electronics, they would probably remember their knowledge in terms of this particular thing. So what it does is that if you shine light on them, it generates the current. And then this is the equation that determines that. And what we have here is IPH is the photocurrent, I0 is the saturation current of the cell, and T is the cell temperature in degrees Kelvin. Q is the charge of an electron, which is 1.6 times 10 to the power 19 coulombs. K is the constant equal to 1.38 times 10 to the power minus 23 joules per degrees Kelvin. And IPH is extremely smaller compared to I0. The ratio of photocurrent to saturation current of 10 to the power 10 range. So this is a standard model that people use for determining the output of a solar panel. And we can draw a picture to show that. And this is where the picture is. And you can see that this shows the cell voltage here and the cell current. And so current and voltage have this graph here. And when you multiply the two of them together, you get a plot that looks like this is the power plot here, which goes up and then comes down here. So this is the maximum power point, which is also called the MPPT. Most of the solar panels operate with MPPT, the solar point tracking. So this is where they want to operate. So there are ways to control that to make sure that you get the maximum output from the solar panels. Now, one drawback of solar panels is that it is a function of the temperature. So if the temperature becomes higher, then you can see the previous equation here, that if this T is the temperature, so it will reduce the output of the solar panel. So basically, the cell power decreases by 0.5% per degree Celsius increase in the temperature. So when in the winter time, when it's cold, you get better output from solar. In the summer, when it gets very hot, the output of solar panel decreases. Now, we have another distributed resource is battery energy storage system. And then, of course, batteries are used in many applications, and the technology is changing rapidly. We used to have different kind of batteries. Now we have the batteries that we have now are very different, and there are more and more applications being implemented of storage in transmission systems as well as distribution systems. Now it's again, those are at a experimental stage. You don't have a large scale deployment. But what we found is that if you want to build a solar system, for example, for a community, which has, it depends on pricing situation. So this example, we had considered that this particular city buys electricity from a third party and sells it to their own residents, and they pay for energy as well as for monthly peak value. So their kilowatt value is very large. And what we found is that the city has a load characteristics which is very high in the morning, and then during the middle of the day it goes down and then goes back up in the evening. So it does not coincide with the solar energy, because their needs are more in the morning and the evening. Middle of the day they are not using as much electricity. So the problem is that if you put solar panels and the cost of demand is not going to be impacted, because the middle of the day your demand is already low, so you are not getting any benefit. But if you couple that with battery, then you store energy during the middle of the day, and then you offset your usage in the evening as well as in the morning, and then you can make that system becomes more economically viable. So sometimes batteries can actually help. Also, in terms of individual homeowners, if they just buy solar panels, depending on the net metering and other rate structure they have, they may not have enough benefit. But if they use battery along with it, then it provides better benefits. It depends on the situation. So, of course, battery storage is becoming important part of the equation here. But of course, the problem is that in terms of the benefits, it takes care of your own requirements, and also when there is an outage, in an emergency situation, you have your own generation available. Like I know that people used to have inverters in their homes, a small battery and inverter to just run one fan and one light when power went out. I think now that is not used anymore because the reliability of supply has increased. But this can help as a backup power when emergencies take place. But the problem is that batteries are not the holy grail because there are issues with other things. But one of the questions that comes to mind, people say, oh, what about vehicle to grid interaction? Because people talk about that. But let me ask you a question that if you have an electric vehicle, would you let utility use your battery? No? Because you're not sure how it's going to be used. So it may deteriorate the life of the battery. So there are warranty concerns and performance and everything else. So V2G is possible, technically feasible, but in terms of acceptance, I think it's a problem because I had own electric vehicle, but I don't want anybody to play with my vehicle. So I don't want to participate in it. But of course, when you have a fleet operator, for example, if you are running, the city has their city buses, for example, they have electric buses, and some of them are just sitting in the parking lot and being charged or discharged. So they can have a contract with the local utility company to kind of arrange V2G. Otherwise, for individual homeowners, it doesn't make sense. It is only for large operators. And then, of course, I think those things we talked about. So typically, the batteries are good under situations where there is high penetration. Batteries can also support solar energy because not only it can store during peak times and use it off peak, but at the same time it also allows to ride through some fluctuations that take place in solar because batteries can smooth out a lot of those fluctuations. Of course, batteries are not like the ultimate solution because the problem is that we used to have lead acid batteries. Now we have lithium ion. And lithium ion batteries are actually environmentally not very friendly because you have to mine lithium, which has a scarcity. So only a few countries have lithium. And I think I've been told that lithium mining is very polluting. So there are a lot of problems with it. It's not an infinite source that you could just dig it and keep doing things. So there are a lot of costs, social costs, environmental costs associated with it. I don't know what will be the future because there are people looking at alternative options. There are new batteries being built with sodium-based batteries and some other technologies. They might have the right solution. At this point, lithium ion seems to be the number one option for most things. But in future, we don't know what would happen. And of course, there are some other battery technologies which are redox flow batteries. But of course, the redox flow batteries require a continuous flow of electrolyte. So they are okay for stationary applications where you have kind of like a building where you put batteries and you connect to the grid. But for mobile applications like your vehicle, they are not going to work for vehicles. So that's only for industrial applications where you have a fixed things. And then, of course, hydrogen is another option that may be in the future. There might be things that can be based off of hydrogen. Anyway, the point is that they are also DC, so they have to be connected through a power electronic interface. So, and then the next one is a micro turbine. These are small turbines which are more like a compressor and a rotator. They run at very high speed, 96,000 RPM, very high speed. and their capacity ranges from 30 to 250 kilowatts. And they are quite very efficient, but I think they are not, at one time, I remember everybody was saying that most people will own their own micro turbine, but it has not happened. So I think they are only used in a very exclusive situations. Are they used in India anywhere?
There are some gas turbines, but I'm not sure about the micro level.
Yeah. So I think, but there are, I think, Europe, some places they use these micro turbines, and then they again produce very high frequency. They produce AC, but they have to again, because they have to be synchronized with the grid, so they have to go through DC and AC, DC to AC. So again, you need IBR for them. And then, of course, electric vehicles are becoming more and more common. In a sense, you can call them a distributed resource, but depends on which way you use it. If you want to put power into the grid from the vehicle, then it's a resource. If you want to use power from the grid to charge your vehicle, then it's a load. So it can be either way. But of course, one of the issue with electric vehicles is that batteries is one issue, which is an environmental issue. But in addition to that, if more people start buying electric vehicles, and then the charging infrastructure has to be built, and then also if you charge things at home, then the load can go very high. The transformers that are supplying people's homes, they will become overloaded. So there are a lot of concerns about that. So at this point in time, it has not really created any issues, but future, as more people start using electric vehicles, that could become an issue. Of course, any kind of distributed resource which has to be connected into the grid will create some issues. So as the penetration or the deployment increases, it causes more and more problems, because the power is flowing backwards from sometimes if there excess generation, it's going to go back into the grid, and then the protection gets messed up. You have issues of voltage fluctuation, because instead of power flowing in one direction, it's going backward, so you can have voltage rise that can take place. So there are a lot of issues. So typically, the utilities are concerned if the penetration goes beyond 15-20%, 15-20% of the load. So they kind of like get worried if that goes beyond that, because it causes a lot of other issues. So IEEE 15747 standard discusses interconnection issues, and they want to make sure that the system operates with the minimum problems. So they have created some guidelines for that, and this is particularly for voltage regulation. And they initially, when the solar PV came into picture, they did not want the PV to be controlled. So they said fixed power factor. You can't change reactive power, just create unity power factor, just produce P, don't mess with Q anymore. But now they are realizing that as penetration of PV is increasing, the reactive power becomes an issue, because you have to control the voltage. And if you want to control the voltage, you need to control reactive power. So they want to allow, or they want to implement control. So these diagrams that you see on the right hand side are basically the RX is the PV diagram, P on the x-axis and Y on the Q on the y-axis, the real power, reactive power, and they define two separate categories, category 1A and category B. Category E is for lower penetration of DER, and category B is for larger penetration with large fluctuations and variations. And what you see here is that this is the operating region that you see let's see, where is that? Right here. This is the operating region for P and Q. And you notice that for a case where you have larger penetration, case B, you are allowed to change Q on the negative side more than in this one. So the basically what they're saying is that P and Q should be maintained within this region. You can the reactive power has a limit. You cannot make it infinite, so it has to be maintained within the area that is specified by this area right here. And then, as far as how to control them in terms of P and Q control, which has to be within the regions that are specified in these diagrams, there are different approaches, control approaches. So 1547, although constant power factor mode or with unity power factor is the default mode, but the distribution system operator can ask the PV DER to change the operation depending on the conditions. Now, this is not for individual homeowners, not for small things, but if you have a bigger PV resource that is connected to the system. Individual homes, they don't have these kind of controls, but in the future that could happen, but at this point, not really. So what you see here is that there are these different modes of operation: constant power factor, volt var, watt var, constant reactive power, volt watt. And for category A, except for watt var, these are mandatory. Well, actually, even volt watt is not required. So these three modes are required, but for category B, all 5 modes are required. So any DER that wants to interconnect with the distribution system, they are required to have these control capabilities. And what are these control capabilities? We can see them in the next slide. So this is the volt var characteristics. So volt is on x-axis, reactive power in the y-axis, and depending on the voltage, we inject reactive power based on these diagrams. So the values of V1, all the values here, they are available in IEEE 1547 standard. And then the next approach is to use, this is what called the watt var characteristic, where x-axis is watt, y-axis is reactive power, and again, depending on how much the generation is, how much P you're generating, you have to generate correspondingly some Q. So if you are generating small amount of P, then don't worry about generating any Q, but as you go past here, then you have to generate, or you have to actually, this is reactive power injection, this is absorption. So you have to actually absorb reactive power, because you want to actually, if you generate more reactive power, then it's going to boost the voltage. So you want to bring the voltage down. So that's why you have to absorb reactive power. So this is what is the watt var mode. And then we have this is the volt watt characteristics. Again, basically based on the voltage, you generate active power, and then this has to follow the graph here. Now, these are two different options. One is restricted to positive real power, another one has positive as well as negative real power. So this again depends on both options are applicable depending on different situations. So again, all these things have to be obtained with power electronics, like what Dr. Dushyant Sharma was talking about, controls. So these controls have to be implemented with power electronics, which are inside of that. And then in terms of, so I already said that These are suggested values of various set points are shown in the figure, but actual values are available in the 1547 guide. And okay, so the DER will provide capabilities of mutually exclusive reactive power control modes listed in the table. So you pick the DER should have capability to implement all of them, but they are mutually exclusive. So either you use either one of them, and that is dictated by the system operator. The system operator will say, okay, you change the switching mode, control mode to this mode, so they will have to automatically do that. 10 minutes. Okay, so these are some interconnection issues. Now I want to talk a little bit about variable solar energy. And so this is one of the issues that we have with solar energy, that on a real nice day, you get output that looks like this. And on a partially cloudy day, you can have an output that looks like this. And a day which is very nice and sunny, but it has a lot of clouds moving back and forth, so it has sharp ups and downs, so you could have a lot of fluctuation. So you have all these things, and how do you handle such fluctuations is the question. So I'm going to talk to you a little bit about, because what happens is that this will create voltage fluctuation, because if your output is PV changing. So this is one approach that I'm going to talk about. Again, this is based on reactive power control. This can be used for even for PV that are at home level, and how these actually will get integrated into okay, these are actually using we have not these slides don't show all the details, but they do use this approach that I'm talking about is based on one of the control mechanisms that I talked about that are suggested by 1547. So what we are trying to do is we are trying to minimize the voltage fluctuations. And as far as the voltage drop is concerned, this is the same formula that I talked to you yesterday when we talked about delta V being equal to Rp times XQ over VR. This is the approximation for voltage drop that we discussed yesterday or Monday. And then, so what we're going to do is we're going to consider a case where there is a line at the end. The line, we have some load here, and delta V is the voltage drop along the line, and the load, there is load as well as generation. So this has both load and generation, both P and Q. So we define Pi to be the difference between generation and load, Qi to be the difference between generation and load. And we substitute those two things into this equation, and that gives you an equation for delta V. And then we come here, and then we say, okay, this is, let's see, so Pi, okay, we have substituted those, so this is the same thing. And then what we are saying is that under an ideal situation, because we want delta V to be 0, because we don't want it to be changing. So if things are ideal, we are trying to approach the ideal situation. So we put delta V is equal to 0. So when you put that to 0, this equation becomes the following, upon kind of like working out this, you get this equation. And then we come to this point, and what we realize is that in this case we need resistance and reactance values of the line, and sometimes these values are not accurately available. So you could actually estimate, replace them by sensitivities. As there is a paper that's available that's listed here, they talk about using sensitivities instead of actual RNX values. This is the sensitivity at bus, voltage sensitivity at, this is, let's see, SVPII and SVQII are voltage sensitivity indices at bus I due to 1 per unit active or reactive power change at bus I. So instead of R and X, we can substitute these values, and then we come up with this next step. This is at time k, and this is at time k plus 1. We have two equations, and then we take the difference between the two, and the equation becomes the following. And then we solar PV is fluctuating. We can assume that the load is not going to fluctuate because load does not change as fast. So we can delete the load values here, LPL. We can assume these to be the same, so they cancel out. The QLs cancel out. So this becomes the reactive power at time k plus 1. So if you have some idea of what the load is going to be at next time instant, then we can provide reactive power to compensate. This is with an ideal requirement that the delta V is going to be 0. So using this option, we applied this formula to a 559 bus system. The details are given in this paper that one of my PhD students published. And then this refers to some figures and thing, but the figures are actually shown in the next slide. These are figure numbers from the book, so I forgot to correct them. But anyway, so this was applied to a system, and then I'm going to show you the results. And I think we are almost getting to the end of the presentation. So this is what you see in this top graph. This is the P fluctuations, and the bottom is the Q. And this Q is computed based on the equation that I showed you. Okay, and the results are shown here. So the original unity power factor is the dotted function, dotted graph here. And the method that we applied is this one, the solid one. And you can see that the voltage has a better values because in this case the voltage is going below the limit for a long duration. And then also you have a tap changer operate here. There's another tap changer operation here. And the voltage is going way up and down in the original thing. But when you applied our control, we can get a much better results. And also the tap operation reduced by 1. Anyway, so this is the last slide, and I think we are at the end of the day. So I think time ho gaya pura? Okay. Questions? Yes. Can you use the microphone? Just a second.
Sir, the similar reactive power control can be used for the wind or something like that also?
It can be used for?
Wind power generation or something.
Wind?
Yeah.
Oh, yeah. Wind actually, the controls can be applied, but again, the problem, this DER that these graphs that I showed you, these control mechanism, all these things, they are not only for solar, they are for any distributed resource. So wind is included in it, batteries, what all kind of resources are included in it. Yeah. This is general for DER, not exclusive to solar. Anything else? 80? 26. All right. 23. Okay, just a second. This one. Okay. It has to absorb. That's right. Yep. What's that again? Oh, what will happen? That I think that they have to.
Sorry, the question is regarding the negative power. So basically, the solar cannot absorb negative power. We have to have a battery or some arrangement that can take that power.
You have to have some mechanism to absorb it. So what they are saying is that solar panels are generating, and you don't want to put that in the grid because there is some limitations. So essentially, what they are saying, they are curtailing the injection of real power. So you have to have your own storage, or you have to have some dummy loads or whatever. Exactly, that's right.
Then goes. Solar panel itself cannot absorb power.
Yeah, because solar panel is generating power, so it cannot absorb it. It has to dump into something else. Yeah.
That's why I thinking it will produce heat and it will damage. So that's why how will it will damage?
It cannot absorb.
It cannot absorb. Okay. Thank you.
That's good. Okay, that's fine. All right, thank you.